our informatics micromodules using dynamic programming to perform global alignment. In this module, we're going to talk about the traceback method that can help us get back the optimal alignments if we have only stored the optimal alignment scores. We're also going to talk about general scoring schemes. To begin, let us look at these two tables again. On the right-hand side, we have the V table, storing the optimal alignment scores of the different subproblems. On the left-hand side, we have the corresponding optimal alignments. The table on the right-hand side was constructed using dynamic programming. For example, for this entry with number 1 here, which I'm pointing at right now, it was determined by considering 3 cases. The first one is to align this G and this G from S into the same column of the final alignment. The second possibility is if we align the G from S with a gap. The third possibility is we align the G from R with a gap. That will lead to the diagonal path, and the horizontal path, and the vertical path correspondingly. After considering these 3 cases, we realize that only the diagonal path can give us this optimal score of 1 for this subproblem. That's why only the diagonal arrow, which is the one I'm pointing at right now, is marked in red color. By knowing that this is the only way to get this optimal alignment, correspondingly on the left-hand side, we also put down the alignment. Sometimes for an entry, for example, this 0 that I'm pointing at right now, there are 2 different arrows pointing in, meaning that there are 2 different ways that can lead to this optimal alignment score. Therefore, correspondingly on the left-hand side, we also see 2 optimal alignments for that subproblem. Now, if we have only stored the table on the right-hand side, how can we actually get back the optimal alignments? The way to do that is actually to trace the red arrows backward. We start from the upper left corner, which stores the optimal alignment score of the alignment of the full sequences, and then we follow the red arrows backward. If there's only one of them, we follow it to construct one extra step of the alignment. If there are multiple of them, we first pick one of them to follow. We'll follow that arrow and subsequently build up a complete alignment. And then we'll come back for the other arrow. So each arrow will lead to a set of optimal alignments. Finally, we're going to reach the lower right corner, and that will give us one optimal alignment. To be more concrete, let us go back to this example. Suppose we only have the right-hand side table. We are at the upper left corner, which is the number 1 here. We ask the question, how did we actually get this number? The answer is, we follow the diagonal path because only that arrow is marked in red. That means in the optimal alignment, the A from sequence R and the A from sequence S should be put in the same column. Then we reach this next entry. Again, there's only one red arrow pointing in, which is the diagonal one. That means we should put this C from sequence R and this first G from sequence S into the same column in the final alignment. Finally, for this number 1, again, we only have the diagonal path. That means we should put the G from R and the second G from S in the same column. That would give us back the optimal alignment of ACG aligning with AGG without introducing any gaps. This is a very simple example, at least in 2 senses. The first sense is that every time we follow just the diagonal, but in general, there could be some red arrows that follow the horizontal direction or the vertical direction. Another aspect that this example is oversimplified is that every time we have only one choice. So now let's look at a slightly more complex example. In this case, we're trying to align 2 sequences, R, which is ATGCGT, with S, which is ACGGCGT. We're still using the very simple scoring scheme, where every match has a score of 1 and every mismatch or indel has a score of -1. This is the complete table, we're not going to fill in the numbers together here, but you can take this as an exercise if you want. After filling in the numbers and deciding the red arrows, finally, we can look at the upper left corner. We see that the number there is 3. That means the best alignment score between these two sequences is 3. Now, we want to find out the best alignment or the best alignments if there are multiple of them. How do we do that? We trace back following the red arrows backward. Starting from the upper left corner, for this cell, there's only one red arrow pointing in, so we have no choice but to put the A from R and the A from S into the same column. Now, when we reach this number 2, actually there are 2 different red arrows. We can follow the horizontal path or the diagonal path. Let's say we take the horizontal path first. If we take that, what is the partial alignment? The way to think about that is, because we are taking the horizontal path, we are consuming one character of sequence S from C to G. That means this C is being consumed, and it is aligned with something, but the T is not consumed yet. So that means this C from sequence S is aligned with a gap. And then we reach this number 3, and there's only one choice to follow the diagonal path, and so on. All the remaining are just diagonal. So this is the whole trace, and the corresponding optimal alignment is like this. We have the first 2 A's followed by a gap in the first sequence, and the remaining will all be diagonal path. That means they are either matches or mismatches. Now we remember that when we were at this cell with number 2, actually there were 2 red arrows. Last time we followed the horizontal one. What if we follow the diagonal one? If we follow the diagonal one, we reach this number 3. Again, there are 2 choices. Either we can further follow the horizontal one or the diagonal one. Suppose that at this point we follow the horizontal one. Then we're going to get the second solution. Notice that the gap position is now at position 3 rather than position 2. And finally, if we follow that same path, but at number 3, we actually follow the diagonal path rather than the horizontal one, then we're going to have this third solution, and the alignment has the gap at the 4th position. Now we complete the whole traceback procedure. So now we have both the best alignment score and all the best alignments that can lead to this score. Now we study another question. So far, we have been considering a very simple scoring scheme, in which every match has a score of 1 and every mismatch or indel has a score of -1. What if we consider other scoring schemes? You may want to ask, why do we want to consider other scoring schemes? There are many reasons. Here, let me give you one reason. If we think about the biology, suppose we are aligning DNA sequences. So there are 4 possible nucleotides, A, C, G, and T. They're actually classified into 2 groups, so-called purines and pyrimidines. A and G are in the same group, C and T are in the other group. If we want to remember easily, we can say A and G correspond to the large nucleotides, and the C and T correspond to the small nucleotides. So if we have a mutation from the same group, for example, from the large nucleotide A to another large nucleotide G, the structural impact is expected to be smaller than mutating that to a small nucleotide. So we believe that because of the smaller impact, this is more likely to happen. And so if we want to put A and G in the same column, the penalty for that mismatch should be smaller than aligning A with C or A with T and so on. So for this same group kind of mutation, we call that transition. And for different group kind of mutation, we call that transversion. So we may want to give a larger penalty for transversion than transition. There are other examples too, but this already illustrated the idea why we would want to use a different scoring scheme. So how can we actually use a different scoring scheme in the dynamic programming algorithm? We're going to use a scoring matrix in the form like this. So we have 5 rows and 5 columns corresponding to the 4 nucleotides and the gap character. And then we can specify exactly what score we want to give if the first sequence has a character indicated by the row headers, and the second sequence has a character indicated by the column headers. In this particular example, we are showing our simple scoring scheme, where all the diagonal entries corresponding to the matches have 1, and all the off-diagonal entries have -1. But of course, we can also design other scoring matrices. So this slightly more general version of the algorithm is called Needleman and Wunsch algorithm. The way to do that is very similar to the algorithm we just studied. So in this initialization step, at the lower right corner, we still have 0. But then for the other entries on the last row and the last column, we need to use the scoring matrix to calculate the score rather than fixing them to -1, -2, and so on. And similarly, for the recursive formula, instead of fixing them to be matched to have +1 and mismatch and indel to be -1, again, we need to look at exactly what kind of match or what kind of mismatch or what kind of indel is there. And then we give the corresponding score according to the scoring matrix. Now let's see a concrete example. The scoring matrix on the left-hand side is based on the idea of transition and transversion. For all the indels, that means all the numbers on the last row and the last column, they're -3, meaning that we think indels are very rare and they should be penalized a lot. The diagonals are still 1, so we prefer matches. But then for the other entries, if it's a transition, for example, A to G, we have a smaller penalty of -1. But for a transversion, for example, A to C, there's a bigger penalty of -2. Now, if we try to align the two same sequences again, the result will be the table on the right-hand side. Again, we're not going to follow all the numbers together, but let's try to do just 1 or 2 of them. For example, if we look at this number 1, how did we get it? We get this number because we consider 3 possible paths. The first path is the diagonal one, meaning that we try to put this T from sequence R and this T from sequence S into the same column of the alignment. So this is a match, and a match has a score of 1. So we have 1 added to the subproblem, which has a score of 0. So the final number along this path will be 1. If we take the horizontal path, we're going to introduce a gap, which according to our scheme has a score of -3, plus the subproblem also has a score of -3. So we're going to have -6. Similarly, if we take the vertical path, we're also going to get -6. So comparing the 3 paths, the diagonal one is the best, so we put down the corresponding number here and mark that arrow red. Let's look at another more complex example. Let's look at this -7. I take this number because there are 2 different red arrows pointing in. So first of all, what is the meaning of this number? This is the optimal alignment score when we try to align GT with GGCGT, the suffixes of the 2 sequences. So again, we have 3 possibilities. If we take the diagonal path, we're going to say we put this G from sequence R and this G from sequence S into the same column of the alignment. Since this is a match, we're going to have a score of 1, and the new subproblem actually has a score of -8. So we're going to have -7 along this diagonal path. If we take the horizontal path, we're going to introduce a gap, which will give us a score of -3. And the new subproblem here actually has a score of -4. So again, we'll get -7. If we take the vertical path, we're going to introduce a gap with a score of -3, plus here, the subproblem has a score of -11. So we're going to get -14, which is lower than -7. Therefore, among the 3 choices, 2 of them actually give the same higher score of -7. So we mark both the red arrows. Now, if we look at the upper left corner, we see that the best alignment score of these 2 sequences is 1 based on this scoring scheme. Now, if we try to trace back, then we can follow the red arrows backward. For the first cell, we don't have a choice. We have to follow the diagonal path. The second one, also the diagonal. But for the third one, we can either follow the horizontal one or the diagonal one. Let's say we follow the horizontal one. Then for the remaining, they are all diagonal. So in this case, the best alignment is like this. After having two matches, or there will be a gap, and then there will be other matches or mismatches. Similarly, if we take the diagonal path first, and then when we reach the number 0 here, we're going to take the horizontal path. That is another way to form an optimal alignment. And here, the gap will be pushed to position 4 rather than position 3. That will give us another alignment with a score of 1. So now with this example, we have seen how we can do sequence alignment with a general scoring matrix.